Hello there and welcome to Lower 6th Further Maths A Level. This is the core part of the syllabus. We're working on Specimen paper question 9. A small comet C is passing near to a planet. The planet can be modelled as a sphere with centre 0 taken from a fixed point in space, so that the motion of the comet is relative to the origin O. The diameter of the planet is 13,000 kilometres. The comet is monitored by a satellite orbiting the planet. When the monitoring begins, the comet is positioned at, okay, so let's start to record this information now, 146,234 minus 85. I always prefer to write my vectors as column vectors rather than ij's and k's, and is moving with a vector, so it's a line vector, so plus lambda minus 21 minus 33 plus 13 for every hour where the units are in thousands of kilometers. Assuming that the comet maintains a straight line course through its motion, determine whether or not the comet will collide with the planet. So, the planet can be modelled as a sphere with a centre 0, 0, 0. So our point is effectively 0, 0, 0. So what this question is asking for here is the distance from a point 0, 0, 0 to a line. So we'll call this the coordinate R. And if the shortest distance from here to here is less than, well, the radius of this planet is the diameter is 13,000, so the radius needs to equal 6,500 kilometers. Okay, so we want this distance to be more than 6,500, so then it doesn't collide with the planet. Okay, so the first thing we need to do is give this coordinate R here a coordinate effectively. The R, that's this coordinate here that I've highlighted, is the point on the line where it's the shortest distance. And as seeing as it's along the vector of our line, it's going to have the coordinate 146 minus 21 lambda, 234 minus 33 lambda, and minus 85 plus 13 lambda. So that's the coordinate for R. The coordinate 0, 0, 0 is where we're comparing it to. So the distance from P to R is the distance from our coordinate to 0, 0, 0, which is just going to be 146 minus 21 lambda, 234 minus 33 lambda, and minus 85 plus 13 lambda. Okay, so now what we need to do is do that dot product rule, and because it's at a perpendicular, or the shortest distance will always form a perpendicular line, the dot product between these two are going to equal 0. So PR dotted with, now we're going to dot it with this line here, the direction vector of our vector, and that's going to be this part here, dotted with minus 21, minus 33, 13. So let's go ahead and do this. 146 minus 21 lambda, 234 minus 33 lambda, and minus 85 plus 13 lambda. And this is going to, dotted with, not equal to, dotted with 21, minus 21, minus 33, 13. And this is going to equal 0. We'll find out the value for lambda afterwards. So what we get from this is minus 3066 when we multiply these two bits together, plus 441 lambda from the double negative, and then we multiply the y parts of this together, which is going to be minus 7722 plus 33 times 33 is 1089 lambda, and then minus 85 plus 13 lambda times by 13, and you get minus 1105 add 169 lambda, and this will equal 0. Solving this to save time, lambda is equal to 7. So the distance, what we can do now is the distance from P to R, or the distance of the shortest point to the centre of the Earth, to the centre of the Earth, we can now plug in lambda equals 7. So P to R, coming straight down from here, plugging in the value lambda equals 7, is going to give us minus 1, 3, 6. So what we've done there is just replace lambda with a 7 value, and we've got this. The way we find the distance now is just to take the modulus of P to R, which is the square root of 1 squared plus 3 squared plus 6 squared, which gives us 6.782. Now, what's the units here? It's in thousands of kilometers, so it's really going to be 6,782 kilometers. Now, the question is to determine whether or not the comet will collide with the planet, so we're going to compare it to 6,500, and the shortest distance on the line of the vector to the centre of the Earth, or centre of the planet, is 6,782. So, no, the comet will just miss the planet. Okay, so that's part A. Part 2 satellites A and B have positions OA and OB at the beginning of monitoring. They return to these positions every 4 hours. Find the expected angle ACB between the comet and satellites A and B when they first return to their initial positions. So if it's every 4 hours, so 4 hours after the comet returns, after 4 hours after these return back to their positions, the comet is going to be at a position of, let's pull out the vector of that comet again, it's 146, 234, minus 85, plus, and it's 4 hours later, once these satellites have returned back to where they are, so minus 21, minus 33, 13, and the planet will, no, the comet at that point is going to be at 62, 102, and minus 33. Okay, so that's where the comet is going to be, and if we want the angle A to C to B, then what we're going to need is the vector from A to C, then the vector from B to C, and the reason we need that is because we need both of these angles to be coming in at C or going away from C to work out this angle here, because that's what the dot product is going to work out for us. So starting off, A to C is going to equal the coordinate for C minus A, so 5, 0, 12, take away 62, 102, minus 33, which is going to equal minus 57, minus 102, 45. The vector from B to C is going to be calculated in a very similar way. Coordinate C take away coordinate B. So that's going to be 54, 54, 12, minus 3. take away, so that's coordinate B, take away coordinate C, which is 62, 102, minus 33. So this is going to give us minus 8, minus 90, and 30. So now we have our vectors that we need for that dot product. So the dot product, so the rule we're going to use is A dot B equals mod A times mod B times by cos theta. So we'll use this one here as our A vector and this one here as our B vector. The direction travelling from A to C and then the direction travelling from B to C. So this is going to be pretty long, but let's go. Minus 57, minus 102, 45, dotted with minus 8, minus 90 and 30. And then it's going to equal to the modulus of the A vector, which is 57 squared add 102 squared add 45 squared, times by the modulus of B, which is going to be 8 squared plus 90 squared plus 30 squared, times by cos theta. And by the time we get round to it, we need to do cos minus 1 of, so it's going to be the dot product of this first part here, which is 11442, and then divided by these two moduluses. So the first one is going to be the square root of 15678, funnily enough, and the modulus of the second one that we'll divide through by is 9064. We then need to do cos minus 1 of this, and we're going to get theta equals 16.3 to the nearest 0.1. Yep, so 16.3 degrees. Perfect. Give a reason why the answer to B may differ from the true value. The reason that the answer B may differ from the true value is that comets generally don't travel in straight lines. They travel in curves, generally don't travel in straight lines in general. Alright then, so 11 marks for that question.